All right, so chapter 7 is all about what we call parametrics, which leads nicely into vector calculus, okay? They're really the same thing. So what does parametric mean? Well, para means two, right? Like the Paralympics, there's two Olympics, right? Yeah. Not really. A parametric equation. Have y'all ever studied parametric equations? It kind of means two in this sense. What we're going to do is we're going to take an equation like y as a function of x, which has two unknowns, right? You graph the x values here and the y values there, and you might get a graph of a parabola or something. What parametrics does is it breaks down the x-coordinate and the y-coordinate in terms of a third variable, which is called the parameter. And a good parameter is time. So if you think about just like a golf shot, right? You're chipping from one point, the ball's going to take flight, go to the other. You might measure x, the horizontal distance the ball travels, in feet, and you might graph that against y, the height that the ball travels, also in feet. Yeah? And would the graph look something like this? Yeah. Okay, the ball's going to travel horizontally, whatever this distance is here, when it hits the ground, and it's going to reach a maximum height of that right there, whatever that is. And it'll reach it when the x value is there. But what you might want to do is break this shot down and measure both the horizontal distance and the vertical height as a function of time. Right, and that's what a parametric equation would do. Now you could graph the height that the ball travels against time, and the graph might look something like that again, right? Because over time the ball goes up and comes down. But now you can also graph the horizontal distance it travels, you know, against time. And what would that graph maybe look like? Yeah, just something like that. Yeah. As time goes on, the ball gets further and further away. And so t would be called the parameter. It gives you more information, okay? Because now you can know when the y value was at a certain point and when the x-coordinate was at a certain point, okay? So those are called parametric equations. And this is what we're going to be doing. We're going to be breaking down these functions. Normally they're given to you already, and we're going to be able to do the same calculus we've been doing, but in a new context. And when you combine the x and y information together, you get essentially vector information, okay? So they're very closely related. So let's look at example 1. It says, without a calculator, make a table, right? Maybe a chart, right? So that y'all are not bringing out your woodworking tools. Make a chart and then sketch the curve, indicating the direction of your graph. So we have a set of parametric equations given to us. X is equal to t squared minus 4, and y is equal to t halves, and we're looking at it on the interval from -2 to 3. So the parameter doesn't always have to be t, but in this case it is, and it doesn't always have to be time, but time is a good one to think about because we know how time works. All right, so what we're going to do is we're going to plot this graph on the same coordinate plane that we normally graph things, on the x and y plane. And so we're going to make a little chart, just like we did in Algebra 1 when we didn't know what the graph of something looked like. We made a chart or a table of values. So I'll do that right here where I can see everything. So we're going to have an x, and we're going to have a y, but I'm going to put the t column on the far left because t is the independent variable for both x and y. Okay, so in this case they gave us the values of t to use. So let's just kind of use the easy numbers, bless you. We'll count by just positive integers starting at -2. So when t is -2, where is the x-coordinate, or what is the x-coordinate? 0, right? And what is the y-coordinate? -1, right? -1. So let's come over here and start graphing what this looks like. So there's my x and y axis. So when t equals -2, we have an ordered pair 0, -1. 0, -1 would be right there. Now notice when I plot the point 0, -1, I kind of lose the t information. We don't show the t information on the graph, but we know that when t was -2, that's the point that we're at. Okay, so then let's increase by one value. You could think of t in terms of seconds if you'd like, and it is sometimes meaningful when we have negative time values. We're extrapolating back in time. So 1 second later, if you want to think about that, we're at -1. And when t is equal to -1, what is x equal to? -3, and the y value is -0.5. Now, just looking at this, notice what happened. In 1 second, my x value went to the left 3 units, while my y value went up 0.5 unit. So you can already kind of get the feel for the calculus part, the instantaneous rate of change. If this is a particle that's traveling along this path, it's moving horizontally faster than it's moving vertically. Do you see that? It's moving left and up, but it's not moving directly left or directly up. It's traveling along some curved path. So let's go ahead and plot that. -3, -0.5. There's -1, -2, -3, and -0.5 will be about right there. Okay, it went left 3 units and up 0.5, but it didn't do that in 2 moves. It didn't go left and up. It traveled through some curved path. All right, in the next second, which would be at t equals 0, the x-coordinate is -4, and the y-coordinate is 0. So now you can see what's happening. Now it only went left 1 unit in that second, so you can almost see like the x is kind of slowing down. But notice it went up consistently another 0.5 unit. So -4 is 0, that's going to be about right here. So it's still moving left and up. It's moving up apparently at a constant rate, and as it moves left, it's kind of, the speed is kind of decreasing. Interesting. All right, let's keep going. We have to go to 3, so at t equals 1, another second later, the x value is -3 again, and the y-coordinate is +1/2. Well, now that's going to be about right here. So what has happened horizontally? In this next second, the particle has, well, I guess somewhere between -1 and 1 for t, this particle has changed directions horizontally. See that? It was moving left. Now it appears to be moving back to the right, and it's moving up again consistently at a 0.5 unit. When t is 2, you plug in a 2, you get 0, and now you get 1. So it's at the point 0, 1. And then finally at 3, it's at 5, 1.5. So 1, 2, 3, 4, 5, and then 1.5. All right, so now if you connect the dots in the correct sequence of t, for increasing values of t, it looks something like this. Oops. Looks something like that. This graph on the x and y axis is not a function of x. It fails the vertical line test. But we're not going to be looking at that or like that anymore. We're going to be looking at this as the path, possibly, that a particle is traveling through a two-dimensional space. And so you could see then that the particle would start at the point 0, 1, end at the point 5, 1.5, but you could see that it got there by traveling along this path. So what a rectangular, or what a, I'll call it rectangular. We're going to call now a rectangular function something like y equals f of x. It's just rectangular coordinates. It's 2 variables, okay? 2 variables. A rectangular graph, y equals f of x, it gives the path. Right? When you see a graph on the x and y axis, you could think of that as the path that an object takes. But it's like walking up to like footprints in the snow where you can't really see the shape of the foot, you just see plunge marks. You can kind of see that there's a path in the snow, but you can't really get an appreciation for which direction it traveled or the speed at which it's traveled. Whereas in this case, when we look at parametrics, it gives us more information. By adding 1 extra variable, we actually pick up 2 other pieces of information. It gives us, of course, the path. We can kind of see the path in the snow there, But what else does it give us? It gives us the direction, yeah. And so the way that we typically show the direction on the graph is we put little arrows like that, just enough to show the direction. Right? It started down here and it traveled in that direction, so we can add that. And then the other thing that it gives us, which is kind of hard to see, but we talked about it as we graphed it, and this is the calculus part, it gives us the speed. We know how fast it traced it out. If you notice, it was never at any point along this time interval from -2 to 3, it was never moving directly left or directly moving up. But those were its components, right, that we found. And then we can infer in between there, it was moving up at a constant rate of a ½ unit per second, but it was moving horizontally quite erratically. It was going left, and then it turned around, and then it came back to the right. And notice it was kind of slowing down as it reached the x-intercept, and then it turned the corner and started speeding up again. Y'all see that? So parametrics give you path, just like rectangular coordinates, but they also give you speed, and they give you directions. Okay? So let's go ahead and see how this would look on a calculator. Go to your calculator now, and you're going to be excited. You're going to do something maybe you haven't done before unless you've been exploring. Make sure you're in radian mode. But if you go down to that whatever fifth line, you have function, which we've been in since little school. But now there's some other options, parametric, polar, and sequential mode. Click to the right to parametric. See what happens. First of all, go to the home screen. Notice now when you hit your X button, notice there's always comma. When you hit your X button now, it shows up as T instead of X. T is the default parameter variable for parametrics. Okay? The theta and the n are going to be your inputs when we get to polar, and then n will be for sequences. All right? So that's what's interesting now when you hit X, you get T. And the other thing that's interesting, hit Y equals. Look what happens when you hit Y equals. It looks a little different now. You have X sub T and Y sub T. So parametrics, para doesn't really mean two, but it works nicely here. It does mean two. Parametrics, you need a pair of equations. So let's go ahead and type in our equations. X was T squared minus 4. Well, that's just the old X button squared minus 4. And then Y sub 1, we'll type in T halves. That's T divided by 2. Now go to your window. Click window. You're going to have extra information. We still have X min, X max, Y min, Y max. That still controls the frame that we're graphing in. But we now have these parameter values. And the default is 0 to 2 pi. Okay? We want to change those. We're going from -2 to 3. So our T min was -2. And the T max was 3. Now the default T step is 0.13. We use 1.0. We calculated a new point every single integer. So if you want to do that, let's see what that would look like. Put that at 1. Now the window, -10 to 10, that should be fine. So go ahead and hit graph. Now because parametric gives you speed, path, and direction, watch carefully when you hit graph. See if you can appreciate the speed and the direction. Oops. I did not go from -10 to 10. Sorry. -10 to 10. There we go. Now do that. Boom. Oh, did you see it even graph? It graphed so fast you didn't see it. Hit the trace button. Notice now it's going to give you your X and Y coordinate and the T value right above it. If you click to the right, this is going to be kind of weird. If you click to the right, look what happens to your cursor. It moves left. That's kind of weird, right? You think it's uncalibrated. But when we click right, we're increasing by values of T, not X's anymore. So that gives you the next value that we plugged in. Click to the right again. Click to the right again, and you can actually see the values that we typed in. And you can kind of see it kind of looks like a horizontal parabola. Go back to your window now. Let's change the T step. Your calculator is much more efficient at computing things than we are. So let's change the T step to something smaller, like 0.1. Now it's going to calculate something every 1/10 of a unit and plot it. Because it's having to do more work, it should slow it down a little bit. You'll still be able to see the relative speed, but it should slow it down enough. Let's see if it's enough to actually see it. Nope. But if you hit trace, now you can see that you're increasing by tenths. Let's go back to the window. Let's slow it down even more. How about 0.01? Now yours probably graphs a little slower than mine, but now it's going to have to do so many more points, it's going to slow it down. If you hit graph, mine actually, I saw it that time. So I'm going to have to slow mine down quite a bit in order to really see it and appreciate it. So let me go 001 and hit graph. And now that's slow enough that I can appreciate it. Boom. And so when you slow it down enough, you get to see the speed and the direction. The direction is always easier to see, but the speed is that subtle nuance. You could actually see that it started slowing down as it reached the x-axis, and then as it turned the corner, it started speeding back up. So that's pretty neat. Now, if you slow it down too much, you know, then you're waiting just for a long time, and you don't really get to appreciate the speed anymore because it's too slow. Or you mess it up. What did I do? 0.0001. It didn't like that. Okay. That was too slow. All right, so you got the idea, right? So what does parametric give you? It gives you three things. Path and direction and speed. Yeah, the direction and the speed are the new ones. A rectangular coordinate, which is what we're referring to now as y equals f of x, only gives you the path. All right, so let's go down to the bottom part. It says, what do you notice now about the graphs of x equals 4t squared minus 4 and y equals t from -1 to 1.5? Well, let's go ahead and do that. Got to go back over here to the calculator. Because I'm going to change my t values, if I left this graphed in x sub 1 and x and y sub 1, it's not going to give me the same path anymore because I'm looking at different t values. So I'm just going to clear those out, and I'll type in my new equations instead of doing it by hand again. We only did it by hand just so you can appreciate it. 4t squared and then minus 4, and now I'll look at t, and now I'll look at the window from -1 to 1.5. And I like the 0.001 for me. So if I hit graph, the path looks the same, and you can verify that it is. And the speed, it kind of looked relatively like the speed was the same. It was slowing down as it reached the x-axis and turned the corner and sped up. But maybe the speeds were actually different. Okay, so that looks the same. Same path, same direction. The speed looked a little bit different. All right, so let's do it for the last one here. Go to y equals, clear that out, and we've got, ooh, this looks interesting, 4 parentheses, 2 sine of t, close that, plus 1, close that, squared, and then minus 4. Wow, funky. And then the next one is 2 sine of t plus 1. And now I'm looking on the window from -1.57, which is pi halves, -1.571. I'll get it. My cursor and mouse are not cooperating. To 0.253. So when you hit graph, let's see what happens now. All right, so it looks like the direction is going to be the same. It looks like the path was the same, but the speed was very different. Okay? And if you think about what the speed is just going to be the derivative of the x and y components. And when you have sine involved, the derivative is going to involve cosine, which oscillates. So this speed was kind of like driving with a really bad driver, like an old person that pumps the brakes all the time for no apparent reason, right? It's going to go fast and then it slows down. And then it goes fast and then it slows down. And then it goes fast and then it slows down. And then it goes fast and then it slows down. So the speeds are like pulsing like that. Fast, slow, fast, slow, fast, slow. Sinusoidal speeds, okay? So what do you notice about all of those? They all have the same path, right? And they did all have the same direction as well. But they had the different speed. You could easily have the path being traced out from starting at the top point and going the other direction. All right, so while rectangular equations on restricted intervals show the path, parametric equations also show the path still, but the speed, which is the one that we're really going to be interested in, because that is instantaneous speed, that's derivative, and the direction. Okay? So there's your introduction to parametric equations. All right, now it says to do the same for these two. And we're not going to do these by hand. But notice there is no parametric interval there, right? You have an x equation and a y equation, but it doesn't give you an interval for t. Okay? So if you're not given an interval for t, you just have to do it for all values of t that work in the domain. All right? So let's go ahead and figure out what the domain is. What's the domain of our x function? We can't divide by 0, so we know t can't be -1, but we also can't have negatives under a radical, right? So t has to be strictly greater than what value? What value gives you a 0? -1. Yeah, so if you let t be greater than -1, you're going to end up with a positive under the radical, and it'll work. And over here, t cannot be -1. So we've already got that taken care of. So that can be your interval then for your t value. So let's go ahead and plug them in. Clear these out. Alpha y equals, remember, is your horizontal fraction bar. 1 divided by the square root of t plus 1. If you hit enter, it takes you to the second equation. And then, very similar here, we got an equation that is a quotient, t over t plus 1. So when I go to my window here, I know I have to be strictly greater than -1, but I'm wondering if I start at -1, if it'll let me do that. What's my t max? Is there a limit to how big t can get? No. So, I don't know. Let's start with 10. We can kind of play around with it. And I'm going to keep this at 0.001. Now, if I hit graph, let's see what happens. Error. Okay, I thought so. Because it's always going to try to graph the first point at the value that you set your t min at. And since it can't be -1, what could I put it as? What's the number that's just to the right of -1? Well, that's way too far to the right. You want to do 0? Let's try 0. Yeah, that's 0. That's a whole unit away. We'll try it. No, it won't be horrible. Oh, man, I do have an appreciation for the speed. It's very slow. It's tracing out a path, and it looks like it's inchworming towards the y-axis. And it's still working. Notice up here it's spinning. It's working. Okay, so no, it's curving. You can always stop a graph by hitting the on button. Just an FYI. I do want to speed it up a little bit. This is way too slow. So let me just take out a 0. Try it again. Oh, yeah, much faster, much better. It's curving. It's curving. Oh, it looks like it's trying to get to the what? It's trying to get to the y-axis. It didn't quite make it. Okay, it didn't quite make it. Bless you. What if I speed it up even more and called it 0.1? Oh, it still didn't make it. Okay, let's try this. What if I change my Tmax from 10 to 20? What will that do? Nothing? Okay. How about from 20 to 200? Ah. Oh, look. When I make, oh, still working. When I make my Tmax bigger and bigger and bigger, this thing looks like it's getting closer and closer and closer to what? The y-axis, and it finally stopped. Did it actually reach the y-axis? Let's see. Trace. Click to the right. Or let's just type in 200. You could just type in 200. Did it get to the y-axis? No. But look, it's at 0.07, and the y value is at 200, 201st. That's really close to what number? 200 over 201. Really close to 1. And x is trying to appear to maybe get closer and closer to what value? 0. So it looks like it's approaching the point 0.01. Okay? Let's see if that's the case. If I go to 2000 here, and I'm graphing at 0.1, that should go pretty fast. Still working. This is where we would normally share spring break stories, but I don't think we have that much time. I'm just glad you all made it back safely. Still working. Oh, except Travis. He hasn't returned yet. Come on. Okay, so I think at least visually we could see that it's approaching 0, 1. Now I'm going to stop it and go back to 200. When I said to pick a number just to the right of -1, I was thinking y'all would pick something not so far away like 0. Yeah, how about -0.9? Let's try 0.9. Let's see what happens. What the heck? Did you see what just happened? No. I all of a sudden picked up this bottom piece below the x-axis. And notice when I hit graph, it like just appeared so quickly. I mean, it just out of nowhere, it just appeared. And then we got to that little caterpillar inching towards the y-axis. Let me change my window now. Let me look a little bit lower. Y min, how about -100? Let's hit graph. Ready? Let's hit graph. Okay, so we know it's approaching 0, 1 as t approaches infinity, but it just stopped. That's where it started. Let's go to the window now. Instead of -0.9, how about -0.09? I went further away. I'm an idiot sometimes. Okay, stop. There we go. -0.99. That's what I wanted to do. Oh, there, whoa! Wow. So how close can I get to -1 without actually getting there? Infinitely close. And as I get closer and closer, it looks like my y values are getting more and more negative. So if I were to interpret this on my paper, this is what I might interpret it as. Here's the point 0, 1. Here's 1. It looks like it's getting closer and closer to 0, 1. And then it looks like it's doing this. That sure looks like part of a what graph? It looks like it could be part of a parabola, right? Now let's see. Let's see what happens. As the limit as t approaches infinity of 1 over the square root of t plus 1 is what? 0. So that means that my x value is approaching 0. I kind of saw that. What would be the limit as t goes to infinity of the y value, t over t plus 1? Yeah, it's t to the first, so it's leading coefficient over leading coefficient. So the y value is approaching 1. So we can get that information by doing old calculus stuff, limits. And we saw that graphically. Now the other thing, as we approached 0, right? What was the limit as t was, oh, I'm sorry, not 0, as we approached -1 from the right-hand side of 1 over the square root of t plus 1? How do we evaluate that? We know it's going to be d and e because direct substitution gives you non-zero over 0, but we also know then that it's some type of infinity. What type was it? Yeah, when you plug it in, -1 from the right, you're going to have square root of a positive number. It's positive over positive, so it's positive infinity. Yeah. So that means the x is going to positive infinity. That means the graph is going out to the right. We're graphing it from right to left, but in this sense, the graph is going out forever to the right. And what would be the limit as t approaches -1 from the right of t over t plus 1? Yeah, now when you plug in, you get non-zero over 0, but you get a negative over 0, which means negative infinity. Okay, so that means that as the t value gets closer to -1, our x values are going out to the right and the y values are going down. And that's what we saw, right? But it's just graphing it the other way. So we do get the direction. Notice I put the arrow on the end. That's just out of custom. That would be a rectangular equation. That's not actually how it's done, is it? It should be like what? It should be like that. That's how the arrows actually should be. And notice the speed. We got an appreciation for the speed. Right here, as t was closer to -1, the speed was what? Fast or slow? It was fast. This thing is coming from negative infinity along this curved path, lightning fast until it hits the x-axis, and then for some reason it like puts on the brakes really, really fast and approaches the point 0, 1 very, very slowly. So you get an idea for the calculus part. So what we're going to do in the next section is simply take the derivative of both of those two functions independently, and we'll be able to figure out the horizontal speed and the vertical speed, which are the component speeds. And when we put them together, we get a component vector, okay? All right, the last one. Do the same for this one. First of all, there's no parameter interval given, so let's find the domain. What's the domain of x? T should be all real numbers, right? Yeah. And what about the domain of y? T should be all real numbers. Yeah. All right, so we are in radian mode. We should be in radian mode all the time in this class. 2 plus 3 cosine. And then -1 plus 2 cosine. So the window, let's see, negative infinity to infinity. How about, let's just go -10 to 10. Oh, we have trig. Let's do this. Let's go -2 pi. Ah, that'll work. -2 pi to 2 pi. And I'll start counting by 0.01. I want to slow it down when I first sketch it. I want to see if I can slow it down enough to see it. And then -10 to 10 should work for the x min, x max, and I'll go back to -10 to 10 for the y min, y max. If you just hit zoom 6 again, it'll reset everything on the x and y from -10 to 10, but it'll also reset your t min from 0 to 2 pi, which wouldn't be bad in this case. So here I'm going to hit graph, and there it goes. Did I do that right? Let me look at my equations again. Does yours look like that? Oh, that's why. Yeah, that wasn't the graph that I was expecting. Sometimes narrating and typing doesn't work for me at the same time. There you go. But notice, what I did have was graphing as a straight line, and it looked like it was tracing it out and pulsing back and forth. That was interesting. This one looks more like, there we go. It's still graphing. Notice that it was still graphing. This one looks like a perfect little what? An oval is what you call it. In little school, we call it an ellipse. An ellipse is just like a circle with two different radius. You have an x radius and a y radius, and they're not necessarily the same. If they're the same, we have a circle, okay? And did you notice the direction that it was sketched? It looked like it kind of got into a loop. Let me see if I can graph it a little bit more accurately. Looks something like this. Did y'all notice the direction? Counterclockwise? Yeah, I didn't catch that. I was too busy, I don't know, looking elsewhere. Yeah, I did break it. I made it too small. Okay, there we go. So, and notice as you extend your t min, t max to -infinity, infinity, it looks like it just gets caught in this endless cycle. Okay, so it doesn't really matter where it starts, depending on your t min. It's going to trace out counterclockwise, and it becomes an ellipse. Now let's get a little bit more information about the ellipse. Let's hit trace, and it looks like I start out over here at 5, -1. All right, so that looks like it's the rightmost point. It doesn't necessarily have to be, but it looks like it. And then it looks like as I scroll, I'm scrolling pretty slowly here. It looks like the high point over here is somewhere around 2, 1. Does it look like it's around 2, 1? Somewhere up here. And if we continue doing that all the way around, this looks like it's at -1, -1, -1, maybe? That'd be the leftmost point. And again, we're just guessing at this point. And then finally, the bottom point, it looks like it's going to be symmetric to the top on the vertical line, so it looks like it's going to be 2 comma something. So 2 comma negative 3, looks like. 2 comma negative 3. Okay, so I know that conic sections is probably not something that you'll spend a lot of time with, but ellipses do have a center. And we have something called the x radius and the y radius, so r sub x and r sub y. Can we figure out where the center is based upon these points? Yeah, horizontally, the center should be the midpoint between -1 and 5, which, remember, if you add them together and divide by 2, you get 2. And then the vertical component of the center should be the average of the y components at the endpoints. 1 and -3, that's, we add them, you get -2. That gives you -1. So the center is 2, -1. From there, you can easily figure out the radius, which is just half the total distance. So from 2 to 5 and from 2 to -1 is 3 units. So the x radius is 3. And the y radius is the distance from -1 to 1 or from -1 to -3, which is 2 units. So let's see if those numbers, the x radius is 3, the y radius is 2, let's see if those numbers are relevant anywhere in the equation. Do you see a 3 and a 2 anywhere in the equation? Yeah, the x radius of 3 appears to be the coefficient of the cosine term, and the y radius of 2 appears to be the y coefficient of the sine term. Okay. Let me switch to highlighter colors now. How about the center, 2, -1? Do those show up anywhere? The x-coordinate of the center is the x constant in the x term, and -1, the y-coordinate of the center, is the y constant. So, do you think those are the same numbers, or do you think that's a total wild, crazy coinkydink? Same numbers. Yeah, those are the exact same numbers. Okay? So, if you recognize that in the future, you got sine and cosine, you're like, oh, okay, that's just going to be an ellipse whose center is at 2, -1, and the x radius is 3 and the y radius is 2. Okay? Now, before we get into the calculus, we'll finish up today. There's one other thing that you might be asked to do, which we haven't been doing. I'm going to come back and do it. You could do something called eliminate the parameter. Okay? So if you have parametric equations, you again have 2 equations, and they have a parameter variable, usually t, but it could be anything. It could be theta or r, z, whatever. Eliminating the parameter essentially gets you back to a rectangular equation. You're getting back to one equation without the t, right? Which means you're going to get a path only, and then you're going to have to restrict the domain so that you get just the path. So let's talk quickly how to do that. If we come back up here and look at these 2 equations, the original ones, I know it appeared to be a parabola that opens sideways. If I ask you to get those 2 as a single equation in terms of x and y, what would you do on your own? Would you have a method? Yeah. It's kind of like what you did when you were solving systems using substitution. You could solve one of those equations for t and then substitute it in the other. I think it's easier to solve the y equation for t, don't you? So t would equal 2 times y. Let me clear this little table, this chart out of the way so we have room. If t is equal to 2y, then I can plug it in over there, and we get x equals t squared minus 4. Well, that's going to be the quantity 2y squared minus 4, which when we simplify it is 4y squared minus 4. Now notice that is a rectangular equation. You're not necessarily going to always have to solve them for y, because your graphs are not always going to pass the vertical line test. But if you think about it, this makes sense. We're used to seeing y equals x squared. If it were y equals x squared, it would be a parabola that opens up. When the squared variable is the other one, x equals y squared, it's a horizontal parabola. And because the coefficient of y squared is positive, it's a positive 4, it's going to open in the positive direction, which is not up, but rather to the right. So if you had studied conics, this would be a real recognizable equation for you. And yeah, notice the -4 doesn't move it down 4. It actually moves the vertex left 4. Okay. So anyway, there it is. Now, if you want to restrict the parameter, if you were to graph this, it would look like the entire parabola like that. If you wanted to restrict it so that you only saw the path that we saw, which was this here, you actually have to restrict the domain. So how do we do that? You use this little thing right here. You just plug in. So when t is equal to, because y is your independent variable, so that's why you're restricting your y values. So all you have to do is plug in. So when t is -2, what is, I'm sorry, let's do it this way. Y equals t halves. Oops. My bad. We'll just plug it in right here. Yeah, that's what I meant to do. So when t is equal to -2, y is -1. And when t equals 3, y is equal to 1.5, 3 halves. So now if you look at it from -1 to 1.5, you get the path that we have, okay? So again, it's not as useful when you convert it back to rectangular because you only get the one piece of information, the path only, and you have to restrict the domain. But it is a nice algebraic activity. Okay, and you're always restricting your independent variable, which is the one that you're not solved for. All right, let's try the next one. If you were to eliminate the parameters here, it looks like it should be a parabola, right? We said it was a parabola? Which one of these do you want to solve for a variable? Yeah, good question, huh? The second one? I'm going to clear all this out since we've already used it. You want to solve the second one? Just because it doesn't have a radical? So if you cross multiply, you get y times t plus 1 equals t. So you get yt plus 1 equals t. You're trying to solve it for t, so you got to get your t terms together. And now you factor out your t, and you get y minus 1 equals -1. So t, did I do that right? Oh, yt plus y. Yeah, thank you. I was going too fast. So that would be -y, -y, -y. Okay. And now you want to plug that in over here? Sure. Yeah, sure, right? Why not? We've come this far. Why give up now? So if you plug that in for t, you get -y over y minus 1 plus 1. That's disgusting looking. No, you weren't wrong. I mean, it's actually working, right? Now, in this case, because it looked like the path of this one is a function of x, this one might be worth trying to solve for y. Okay, so let's not give up yet. Let's square both sides. So we get x squared, and then 1 squared is 1, and we square the bottom, and we get the radicand. Yeah. And now, if I multiply, these two can switch places. So -y over y minus 1 plus 1 equals 1 over x squared. This is still kind of gross. So now, let's call 1 y minus 1. So we get -y minus y minus 1 over y minus 1 equals 1 over x squared. And that's -2y minus 1 over y minus 1. Why did we do it this way? I don't know either, but we're going to keep going with it. Now let's, -2y, I'm going to cross multiply. -2y minus 1 times x squared equals y minus 1. What's my goal? What am I trying to do? Solve for y. So I get -2x squared y minus x squared equals y minus 1. So now I can get my y terms together. So I'll bring this over here and this over here. So I get 1 minus x squared equals y plus 2x squared y. Yeah, we maybe should have done it the other way. And if I factor out the y, I get 1 plus x squared. And now I get y equals 1 minus x squared over 1 plus x squared. I feel like I messed up somewhere. Does it? It's supposed to be a nice equation of parabola. Here, let's try this. I'm not going to say that that's wrong, but I'm just going to leave that over there, and let's try the other way. Let's solve this one for t. I can, again, switch those out, so I get the square root of t plus 1 equals 1 over x. And now if I square both sides, t plus 1 equals 1 over x squared. T equals 1 over x squared minus 1. So if I plug that in over here, I get y equals 1 over x squared over 1 over x squared minus 1 plus 1. That doesn't look right either. Oh, this is 1 over x, sorry. 1 over x squared, I forgot the minus 1. Yeah, okay. So now on the bottom, those cancel, and I get 1 over x squared minus 1, and then instead of dividing by 1 over x squared, I'll multiply by its reciprocal x squared. And if I distribute now, x squared over x squared is 1 minus x squared. That looks better. Yay! Because now we recognize that as a parabola that opens down with a vertex at 0, 1. Yeah, and that's kind of the parabola that we thought. So in hindsight, maybe, you learn from mistakes. Since it looked like it was a function of x, and I wanted to solve for y ultimately, maybe that's the one I want to be plugging into, so solve for the other one. Now, we do have to restrict the domain. Since x is our independent variable, all we have to do is figure out what values of x we need. So we set our t values. Yeah, it would just be, all greater than 0. So we could just say x has to be greater than 0. Yep. Because when you plug in any values of t that are bigger than -1, you're going to get positive values. So x can be anything bigger than 0. Okay, so that worked twice on example 1 and example 2. How do you think we're going to eliminate the parameter on example 3? If I have to solve for one of those t variables, I'm going to have like an inverse sine or an inverse cosine. Okay, so solving for one variable works well when you have functions, like rational functions, polynomial functions. But if you have trig functions, guess what works? Identities. Okay, and since we have a function of sine and cosine, what identity do we have that relates sine to cosine? Pick one. Pop a pid. I like it. Cosine squared plus sine squared equals 1. This is true all the time, right? So instead of solving one for t, let's just solve this one with cosine of t in it for cosine of t. So I get x minus 2 divided by 3 equals cosine of t. So if I plug in then, I get x minus 2 over 3 squared, plus we'll do the same thing for sine. If I solve this for sine, I'll add 1 to both sides and divide by 2, and that equals sine. And so I can plug that in here. Y plus 1 over 2 squared, and that equals 1. And now if I simplify, I get x minus 2 squared over 9 plus y plus 1 squared over 4 equals 1. And this ends up being the standard form for an ellipse. Okay? It's x minus h squared over r sub x squared plus y minus k squared over r sub y squared equals 1. This is called the standard form for an ellipse. The center is always at hk, and of course the x radius is below the x squared term, and the y radius squared is below the y term. So look what we can get straight from that. It's x minus 2 y plus 1, so the center should be at 2 comma negative 1, and the x radius is 3 and the y radius is 2. Okay. So again, I don't think that you've studied conic sections in great detail, but if you had, this equation of a standard form of an ellipse would be very recognizable to you when it equals 1. Okay, so if you had two equations that had like a tangent and a secant in it, you would use baby PID number 1, 1 plus tangent squared equals secant squared, and the same thing if you had like a cosecant and a cotangent. So the trig functions of Pythagorean identities work great. All right, so I think we'll stop right there for today. That's 1, 2, 3. Tomorrow, we are going to bust out the calculus. I'll show you how to take derivatives of parametric equations. You kind of got the idea so far, and then we'll see how it relates to vectors. Okay, so that's tomorrow. Big day tomorrow, we'll bust out the calculus. Don't forget your worksheet for improper integrals is due.